All right, we're going to go ahead and get started. Thank you everyone so much for joining today. My name is Bonnie Beniwol. I'm the Natural Sequestration Initiative Manager at the Climate Center, and I'll be moderating today's webinar. This is the second part of a 6-part webinar series organized by California Environmental Voters, Project 2030, and the Climate Center. In case you missed our first webinar on the science behind carbon removal, my colleague Pamela will drop the link in the chat now so you can check it out later. Next slide, please. Now, in today's webinar, we'll be discussing the various strategies out there that can remove legacy carbon emissions from the atmosphere, from nature-based solutions all the way to fully technological approaches and many of the ones in between. The slide here is a visual illustration of the range of strategies that we're talking about to give you a visual of the wide variety of CDR or carbon dioxide removal approaches that exist. Now, I want to acknowledge that each of these strategies could have an entire webinar dedicated to them, or even a webinar series for that matter. But for today's purposes, we want to give you all a 30,000 foot overview on each strategy. How does it work? What is its current status of deployment? And what are some of the pros and cons for each one? Now, because the content here is so vast and deep, and the speakers have a limited amount of time, we'll be dropping links to additional resources in the chat throughout the presentations so you can dig into each topic in more detail as you wish. Now, that being said, we are hoping to share enough information to give you a foundational understanding of each approach, so you can consider this as a sort of speed dating exercise when it comes to CDR approaches. Now, before we dive into the topics at hand, I want to take just a few moments here to to orient us on the context and intent behind this webinar series. Next slide, please. So first off, why are we even talking about carbon dioxide removal? Now, 6 years ago, the IPCC gave us a prescription for what we have to do to avoid climate catastrophe. We have to cut emissions in half by 2030 and draw down 100 to 1,000 gigatons of CO2. The IPCC considers carbon removal as inevitable to meet our Paris Agreement goals. Additionally, California's AB 1279, signed into law in 2022, set a state goal of reaching carbon neutrality by 2045, with at least 85% of that coming from emission reductions, and therefore up to 15% from carbon removal to meet that net zero goal. California also has set a goal for CDR in its 2022 scoping plan. Next slide, please. Since many CDR projects are being proposed and permitted here in California, communities must have a critical role in if and how these projects get developed. And lastly, many CDR pathways provide the necessary co-benefits for adaptation, such as biodiversity, food and water security, clean air and water, and more. Next slide, please. So our 3 organizations, California Environmental Voters, Project 2030, and the Climate Center, have developed some shared principles as we learn together about carbon removal and the kinds of steps that need to be taken. Number 1, removing past climate pollution from the atmosphere is essential to stabilizing the climate. Number 2, we must rapidly accelerate the cutting of greenhouse gas emissions and the phasing out of fossil fuels. Number 3, CDR is not a substitute for direct emission reductions and is distinct from carbon capture and storage, which is a technology that aims to capture carbon at the point source before it is emitted into the atmosphere. We're talking here rather about removing the existing atmospheric carbon. Number 4, CDR projects should be community-centered and designed with input from communities where these projects are to be sited and where the transportation and storage of the carbon will take place. Number 5, CDR projects should prove that they are not exacerbating any existing environmental problems. And finally, the role of nature-based carbon removal is critical with its many co-benefits, as I mentioned. Now, with that context being set, I want to share just a few more notes before we dive in. Next slide, please. We will first hear from our 7 fantastic speakers, and then we'll have some time at the very end for Q&A from the audience. So please input your questions into the Q&A feature in the Zoom and not the chat. This will make our job of coalescing all of the questions so much easier, and we can then leave the chat open for sharing resources and comments. Second, we know that the CDR space comes with a lot of jargon, so we'll be dropping a link in the chat now to a glossary of terms that you can reference throughout the webinar if needed. Additionally, please mark your calendars for our next webinar in the series on CDR and communities on November 15th. And last, but certainly not least, I want to say that we've heard some excellent and helpful feedback after our last webinar, including that it did not provide adequate perspectives from environmental justice groups or other stakeholders that have some concerns or are opposed to some forms of carbon removal. So we firstly want to acknowledge that. And secondly, we have invited speakers today that can share more of that perspective. We will first be hearing from our colleague Asha Sharma, who will speak about community concerns. Then later in the webinar, we'll hear from our speakers that can share a more critical lens on the technological approaches, including BIKERS, which stands for Biomass, Carbon Removal and Storage, and DAC, which stands for Direct Air Capture. Now, these topics are not easy, nor are they straightforward. So this is intended to shed light on some of the debate that is going on with some of these CDR strategies. So you as the audience have a more holistic picture of the portfolio of solutions that we have on hand. Next slide, please. So here is a slate of experts that we have joining us today. I'd like to first invite Asha Sharma to turn on her camera and join us. Asha is the State Policy Manager at Leadership Council for Justice and Accountability, where she develops and manages state policy campaigns driven by community needs and priorities. Asha, the floor is all yours.
Thank you so much, Bonnie, and thank you for having me today. As Bonnie mentioned, my name is Asha Sharma, and I'm the State Policy Manager of Leadership Council for Justice and Accountability. We work in partnership with communities in the San Joaquin Valley and Eastern Coachella Valley in California to achieve justice and a healthy environment, including clean air and clean water. I want to thank our partners at the Central California Environmental Justice Network, Central Valley Air Quality Coalition, the Center for Race, Poverty, and the Environment, and Physicians for Social Responsibility LA for their tireless organizing efforts with communities to sound the alarm about the risks of carbon capture. Many geological carbon capture and storage projects are being cited for the San Joaquin Valley, a region that already has some of the most polluted air and water in the country and is home to some of the most polluting industries in California. Many carbon capture and storage and transportation projects carry serious risks for surrounding communities, who are oftentimes environmental justice communities that are already overburdened with polluting and risky industries. Carbon dioxide, if leaked, displaces oxygen, causing asphyxiation of nearby residents. Carbon pipeline leaks have already occurred multiple times in Gulf Coast states. Residents have had seizures, and many now have long-term respiratory and neurological impacts. Leaks can also contaminate local groundwater, and these technologies require the build-out of miles and miles of carbon dioxide pipelines through communities. Bioenergy and biomass conversion can also harm health by releasing toxic air pollutants into the environment. For example, the Desert View Power Plant in Mecca, California, has been cited for multiple violations of environmental law, including the release of mercury and carbon monoxide. These toxic air pollutants will not stop just because a plant becomes equipped with carbon capture technology. Carbon capture technologies will simply perpetuate the pollution that accompanies fossil fuel extraction, bioenergy plants, and other harmful industrial processes that are already poisoning environmental justice communities. To illustrate this, the Direct Air Capture Hub feasibility study in Kern County is currently being led by an oil and gas company. We must solve the climate crisis, but not at the expense of the health and safety of our communities. Pushing and subsidizing these harmful, energy-intensive, and expensive technologies takes away much-needed investments from the transition away from fossil fuels and the co-pollutants that accompany their extraction. Research shows that investments in a rapid transition away from fossil fuels towards renewable energy would allow us to meet our climate goals without risky carbon capture technologies, and that much greater reductions in greenhouse gas emissions would occur. We must instead increase investments that would ensure a just climate transition. These include increasing access to affordable renewable energy in people's homes, clean public transportation in both rural and urban geographies, investments in the grid capacity necessary to allow for affordable electrification, and job training and support for displaced workers. California is the second largest natural gas consuming state in the country, was the seventh largest crude oil producer in 2023, and ranked third in crude oil refining capacity. We do not have time left to delay our transition away from fossil fuels. We need to double down on investments in proven community-supported climate solutions, not risky technologies that will only distract from the deep decarbonization needed to achieve our climate goals. Thank you.
All right. Thank you so much, Asha. Really appreciate your remarks, and we'll certainly be digging more into some of what you mentioned later in today's webinar, as well as throughout the series. Now, we're going to get into the overview of strategies. So first, we will hear about ocean-based carbon dioxide removal with Akash Rastogi from Ocean Frontier Institute. Akash is kindly stepping into for his colleague Anya Waith, who has unfortunately come down with COVID. We're wishing Anya a speedy recovery, and Akash, thank you so much for stepping in. While you come on camera and pull your slides up, I will tell the audience a little bit about you and the Ocean Frontier Institute. OFI is based in Canada and led by Dalhousie University. It is a global leader in interdisciplinary research and unites researchers, industry, and government to solve complex problems. Akash is the lead strategist at OFI, focused on advancing its innovation and commercialization mandate. He is a founder of the Reykjavik Protocol, a member of the Canadian National Carbon Management Coalition, and a mentor to numerous ocean-based CDR startups. He's a graduate of the Indian Institute of Technology, the University of Western Ontario, and the Stanford Graduate School of Business. Akash, welcome.
Thank you. And again, apologies to everyone for having listened to me instead of Anya. You're missing out a lot. I can tell you that for a fact. So today we're going to talk about ocean-based carbon removal, or as people in the industry call it, MCDR. And one thing before we start digging in, is want to state is, as Bonnie just explained in the intro, OFI is a science-based organization, and scientific rigor is at the heart of everything we do. We are agnostic to a given specific MCDR pathway, and we see tremendous potential for what MCDR can do in terms of amount of carbon that can be sequestered and removed durably from the atmosphere. We also believe that it needs to be done in a very responsible and staged manner, so that we have a better handle on both the direct and indirect consequences or impacts from any of the deployments. So with that, next slide, please. Can we go to the next slide, please?
Yeah, sorry, it's giving me a problem here.
Okay, so while you're waiting for that, so just as in terms of definition, MCDR refers to a collection of approaches or pathways that essentially are either amplifying or accelerating the naturally occurring biogeochemical processes in the ocean. And as some of you may know, oceans play a central role in regulating our climate, and is essentially leveraging those existing processes. Next slide, please. So a lot of people tend to distinguish different pathways in MCDR into biotic versus abiotic approaches, and that has merit. We like to also distinguish between what we call coastal blue carbon and deep blue carbon. Coastal blue carbon essentially refers to solutions using mangrove, seagrass, kelp, and so on, and these are coastal ecosystems. And deep blue carbon refers to the carbon that's seaward of coastal systems. And so you start thinking easy and high seas and deployments in those areas. And both of them are unique in terms of the potential of how much carbon they can sequester, the durability, but also the risks that they can potentially create from any of the deployments. And for us, it's important to delineate between the two, as what's really required to get them to scale effectively will actually vary as well. So next slide, please. So just talking about, some sort of a comparative analysis, there's this concept called carbon time machine. As we all know, we need to get to carbon concentration levels in the atmosphere to pre-industrial levels, right? And CDR is a collection of different approaches, as was said up front. And so here's a simple concept to show a relative potential between different CDR pathways, which is, so if you, in terms of how much of an impact can have in moving the clock back from a carbon concentration time perspective. So the first one, we see the tree. I'm going to go from left, the first image, which is you see afforestation. So 100 million trees, they essentially move carbon clock back by 34 minutes. The second one, if you take it as an example, is about 8,500 hectares of Panama mangroves, which will be coastal blue carbon, that moves the clock back by 24 seconds. 18 DAC units, the current scale, they probably move the carbon time machine by 8 seconds. But compare that to a 1% increase in natural carbon sequestration potential of deep blue carbon or ocean CDR, that moves the time by more than 3 months, by more than 3 months. So there is a significant impact or differences between the different CDR approaches purely from a carbon sequestration potential. Can you move to the next slide? So here's a simple pictorial view that some of you may have seen in the past. And essentially, it's talking about different types of MCDR pathways. Some are biotic, and some are abiotic. And you've probably heard of macroalgae sinking, you heard of ocean alkalinity enhancement, nutrient fertilization, artificial upwelling, downwelling. And so they all are very unique. And there's a tendency for a lot of people, especially outside the MCDR community, to clump them together. But they all offer very unique risk-reward trade-offs and potential. And so it's really important that we actually look at them uniquely and not clump them together. Next slide, please. So what is the state of play? So let's talk about the upside, like why MCDR does matter. I think as Bonnie was mentioning in her intro, carbon removal is no longer a luxury. It is a necessity. And how much carbon do we need to remove, of course, varies by the speed at which we decarbonize, which is the most important lever, right? But the amount of carbon we need to remove ranges from 6 gigatons to 14 gigatons a year till 2050 based on the speed of decarbonization. The consensus view is around 10 gigatons a year, and then it ramps up to 20 gigatons a year beyond 2050. So if you look at all the carbon removal approaches collectively, globally, we are probably sequestering in the order of 40 to 60 million tons a year today. And if you start accounting for amount of carbon CDR that's actually high durability and also net negative, that we boil down to about 10 million tons a year. So we need to scale up by more than 1,000x really to get to our goal. And that's where MCDR becomes truly relevant. It is in a nascent stage today, as you will probably learn in the next few slides. But if you look at all the MCDR pathways collectively, the floor for how much carbon it can sequester is about a gigaton a year. And the cap is somewhere in 4 to 5 gigatons a year. So it's in multi-gigatons for sure, right? And that's why it really matters, is that's the step change in an improvement towards getting a 10 gigaton a year carbon removal targets. So that's the upside. If we go to the next slide. We are at a very, very nascent stage, I would say. Most of the work that's happening is either lab level or small scale field trials. And the amount of, even if the field trials, and there are a whole bunch of them actually happening globally, they range from, 100 tons of carbon removal to 1,000 tons. So it's tiny, small scale right now. And of course, one of the main objective of these field trials really is to start better quantifying the impact of any of the perturbations happening in a given specific pathway. Next slide, please.
We just have 1 more minute for this section, Akash.
Okay, all right. So there are many structural impediments that we need to overcome in MCDR pathways. A big one is governance, policy, and regulation, starting from domestic to all the way to international. And in the international arena, there's a work happening on London Convention, London Protocol area, which is evolving very fast. The second area I would say is standards, and Reykjavik Protocol is one of the standards, but then recently Isometric released standards for archenetic enhancement. And so there's some progress on that, but a lot more needs to be done. Next slide. Social license, a big challenge in this area. I think Asha was already alluding to a lot of important points that apply here as well. And there needs to be a lot more concerted effort in terms of effective and honest and transparent and proactive some social licensing for MCDR deployments. And there's been some misses, but there's been some positives as well in this space for the deployments that have occurred to date. Next slide. The oceans are changing, but I don't think we have a strong handle on understanding how they're changing. And that has massive implications for the carbon budget or carbon flux in the oceans. And so it's really important that we have the science and scientific rigor to truly understand and quantify the changing oceans. Governance standards and protocol, absolutely critically required, and a lot more effort needs to happen there. And MRV, one of the biggest stumbling blocks right now to really have credible additionality carbon sequestration assessments for any of the deployments. That's a big challenge, especially as you think about open systems and deployments ultimately in EEZ and high seas.
Alrighty, Akash. I'm so sorry to cut you off, but we do have to move on. Thank you so much for that wonderful presentation. And the slide decks will be available afterwards as well. And we can answer more of the questions during the audience Q&A portion at the very end. But thank you so much. That was a great overview on the vast world of marine-based CDR. And there is so much more information to learn about each of the strategies that Akash described, from ocean alkalinity enhancement to upwelling, blue carbon, and more. So we're dropping a link in the chat now where you can learn more about each of these strategies within the broad category of marine CDR itself. Now, next up, I will invite Dr. Charlotte Levy to come on screen and share and to talk about land-based strategies. Charlotte is a managing research advisor at Carbon 180 and is dedicated to scaling up carbon removal while ensuring that these solutions are rooted in justice and accountability. She received a PhD in land use management for climate mitigation from Cornell University and has worked in policy from grassroots community advocacy to federal climate and energy policy. Charlotte, the floor is all yours.
Thank you so much for having me here today. I'm really excited to get to talk about carbon removal strategies that make use of land. So the natural solutions portfolio, these are often called. There's a lot to cover today, so I'll also be trying to reference other sources that I would suggest to folks. And please feel free to reach out to me with any questions and ask questions today. So what is land carbon removal? There's a lot of things that fall into this broad category. One of the first places that we tend to look is farms, because there is so much managed land that is used to produce crops and food and fuels and fiber. There's a number of agricultural practices that can be used to store carbon in soils. When plants grow, they are able to draw down carbon from the atmosphere, and in the process of growing and dying, they transfer that carbon into the soils long term. So trying to enhance and improve that process. There's also carbon storage in forests. Again, as plants are growing, they're storing that carbon in their embodied form. And so we're able to grow forest spaces out, and that helps to build carbon into the trees themselves and into the soils. And finally, I added a little bit of a wildlands category. I won't have time to go into this much today, but there's also potential to restore wetlands and grasslands, as well as important soil carbon sinks. So thinking about removal through farms, how does this work? Carbon is naturally stored in soils over time. However, many agricultural processes actually deplete a lot of the carbon that would be stored in those soils. The reason for that is because there's a lot of processes that are intended to help enhance the growth of the plants, but which also come at a cost of the carbon storage in the soils. As a result, over the past few centuries, we've seen quite a loss of soil carbon globally, and especially in the United States. If you think about the most productive agricultural parts of the United States, they also tend to be areas that historically were in grassland or in some other form of land use that built a lot of carbon over time. And so we're actually kind of spending out an account that was stored over centuries of previous natural use. Therefore, there's a lot of incentive to have better stewardship of US soils to try and rebuild carbon and get back to more of that high carbon storage natural state. We believe that because there is so much soil to work, so much agricultural land to manage, there's the potential to store as much as 13% of domestic greenhouse gases. But I want to say that that comes with some big ifs on what kind of techniques we use and how we actually manage it. I've been throwing management out a lot. There's a broad suite of tools that we could use to try and store more carbon in soils. These are some of the general categories that we tend to work on. Especially, I'd like to highlight that there's the potential to add soil carbon amendments. So that might include compost, mulch, and biochar, which I know is very relevant in California. We'll be talking a little bit more about biomass and managing that. And that can help to increase the organic carbon levels in soils, as well as helping to promote the health of crops. Another thing that I'd like to highlight is agroforestry, because our team actually works quite a lot on this and has done a lot with policy recently. The intent here is to create agricultural lands which are making use of both forested land and cropland techniques. So you might be adding trees to pasture land to provide shade for cattle, or you might be adding a buffer to create a windbreak that adds a little bit of forest of trees within the cropland itself. So I understand that biochar is really important in California. I jumped a little bit ahead because I thought we were going to have talked about the BEC solutions first, the biker solutions first. Biochar is a really important tool for carbon removal. It is what it actually is a very charcoal-like substance. If you've ever handled charcoal, you have a good idea of what biochar looks like. That is made from taking biomass, that's any organic material grown by a plant, and heating it under very specific conditions. That helps to really turn that what was a green material into something that's concentrated into the carbon, making it a very efficient way to store carbon in soils. It's also beneficial to add it to soils because it can help to increase water retention, and it creates a very suitable habitat for microbes that act in the soils that can help in general to make nutrients more accessible to plants. So that creates a lot of co-benefits and a lot of incentives for applying biochars to soils. But I'd also like to emphasize that while we understand how to create biochars very well, using generally the sort of technologies that are used for, have previously been used for bioenergy, that's heating the biomass under very specific conditions, we don't know as much about how to apply these well to soils. And so there's a need to be interfacing with farmers and thinking about how to apply biochar in a way that is creating the most benefit to them and that is sustainable in the long term. All right, so just a little bit of framing on farms. This is my more technical slide. If you're interested, I put the citation here, but what this is really saying is that this blue line is the kind of range of carbon that we'd expect to see stored in soils that have been left alone. These are the unmanaged grasslands that have made up a lot of the central part of the United States historically. And then if we look at the bottom line, the black line, those are the agricultural lands that humans are actively managing. And you can see that under the same conditions, we are storing so much less soil carbon. And so when I talk about like what's the potential of carbon removal through agricultural management, the ideal might be to get to this so-called biological limit, what we've been able to see soil store historically and what unmanaged lands are still storing today. And then the red line is sort of that theoretical maximum, thinking about what we can do to really innovate and create a managed agricultural system that maybe is storing even more carbon than it would have done in an unmanaged setting, really pushing the limits of how much carbon can be stored through soils. So if you're interested in learning more, my organization, Carbon 180, has pulled together a number of reports that talk about how we can lead on soils, what our goals for soils are. These outline a lot of plans. Some of them have to do with working with producers to really understand what the needs are and how to create processes that are helping to not just store carbon, but benefit farmers. And on the other side of that, we have more of the technical aspect where we need to be able to measure and understand how much carbon has been added to soils so that we can see if our techniques are effective, make sure that we're not taking too big a hit on yield, and thinking about how to move forward and measure this in the long term. All right, so now I'm going to jump into forests, which I think we've touched on a little bit. So forests also have an enormous potential to store carbon, are already storing a lot of carbon. However, they're also really under threat right now. If you looked in the news, if you've looked outside potentially, you may be aware that a lot of the forests in the United States are under threat from severe wildfires, from pests and diseases, deforestation. Land use is always a pressure. So we believe that managed well, U.S. forests could sequester and store at least 10% of annual U.S. emissions on top of what they're storing today. However, we have to recognize that currently they're not on track to do so. We are losing the ability of forests to store carbon a little bit every year. Some of the management practices that we try and work on and encourage are, first of all, just starting with forest conservation. Many people aren't aware that even an old age stand is usually continually adding a little bit more carbon each year. It takes a very long time, centuries, for forests to even come close to maximizing the amount of carbon that they can store, although the fastest growth rate is right away. Additionally, we can be planting new forests, afforestation, reforestation. The difference here is whether or not we're planting forests where they have been historically or in a new place. And then finally, thinking about what some of those threats are to forests, we can try and manage to protect against them. That's thinking about prescribed fires to protect against larger wildfires, pest and disease control, and managing fuels that exist in forests.
Hey, Charlotte, we are at times, if you can just take about 30 seconds to wrap up.
Absolutely. All right, so last thing that I want to raise is that our forests are under threat. We want to think about the fact that, especially in California, and this is a figure that I pulled specifically for the area, there is an enormous potential to lose forests because of fires. So thinking about how to build that resiliency is a really important part of our climate smart management strategy. And if you'd like to learn more, again, there's resources available on our website. We'd love to talk to you. All right.
Perfect. Thank you so much, Charlotte. You covered a lot of ground there, from soils, biochar to forestry, and really appreciate you including the additional resources in your slides as well. Up next, I will invite Dr. Daniel Sanchez to come on video and share his screen and talk about biomass carbon removal and storage. Dan is a professor at UC Berkeley's Department of Science, Policy, and Management, where he runs the Carbon Removal Lab. He studies engineered biomass and bioenergy systems that remove CO2 from the atmosphere and is also a principal scientist at Carbon Direct. Dan holds a PhD and master's from UC Berkeley as well. I also wanted to note that, as was mentioned, we are putting the full bios of all the speakers into the chat so you can check out more information there. With that, Dan, please take it away.
Hi there, everyone. Thanks for the opportunity. Again, my name is Dan Sanchez. I'm a faculty member at UC Berkeley, and I also work in the private sector with a company called Carbon Direct. What I wanted to do in the 7 minutes I have was very briefly introduce biomass carbon removal and storage, which I think is a broad concept, as Charlotte already alluded to, and how it may play a role in carbon removal, specifically within the state of California. So I just want to start with a little bit of context around what we mean when we're talking about sucking carbon out of the atmosphere. At the broadest sense, there's two ways that we can do that. We can use biology and things like ecosystem management, soil management, agriculture in order to pull carbon out of the air. Or we can use engineering or large kind of chemical systems in order to do that. On the biological side, we're talking about restoring and managing terrestrial lands, or restoring and managing aquatic ecosystems, storing more carbon in soils through changed agricultural practices or biochar addition. And then on the right, we have kind of these, large chemical processes, things like direct air capture that use large machines to suck CO2 directly from the atmosphere, or mineral weathering, which involves mining and exposing those materials to the air. Um, I work specifically on what I consider to be kind of a hybrid carbon removal approach. And this is ones that use both biology and engineering and chemistry in order to suck CO2 from the air. I think the two most prominent ones that we hear about kind of come under two catch-all phrases. One would be bioenergy with carbon capture and storage. That's also known as BECCS to folks in the audience to follow closely. Another opportunity also involves sequestering carbon in biochar, which, as Charlotte mentioned previously, is a recalcitrant form of carbon derived from biomass that can be either added to soils or to long-lived materials in order to durably store CO2 out of the atmosphere. So let's take a little look at what we mean when we talk about bioenergy with carbon capture and sequestration in particular. And I want to walk through this figure from left to right. Typically, when we start thinking about a bioenergy with carbon capture and storage or a biomass carbon removal process, we start with typically lignocellulosic biomass. This is, inedible biomass, most plentiful natural material that we have on the planet. And when those grow, that sucks CO2 out of the atmosphere. That biomass is then harvested and transported to a conversion facility where we can use a range of approaches, including thermochemical conversion using heat and catalysts, or biochemical conversion using biology in order to turn the carbon in that biomass into useful products. Typically, when we're talking about bioenergy with carbon capture and sequestration, there is both an energy product and a carbon product. The energy product can be heat, transportation fuels, liquid or gaseous, electricity, other energy products that we can make from biomass. And the carbon co-product is typically CO2 that is captured, compressed, and geologically sequestered several thousand feet underground, where we expect it to stay for centuries and millennia, and again, stay out of the atmosphere. There are, of course, lots of variations on these approaches. Some of them use carbon storage in other durable forms rather than geologic CO2 storage. Some emerging biomass carbon removal processes don't even make co-products. They're really just focused on locking up the carbon that is in biomass for its carbon removal value. But again, just from left to right, we're talking about growing and harvesting biomass, converting it, and making valuable products, including carbon storage. I think everyone understands the role that carbon dioxide removal could potentially play in stringent climate change mitigation scenarios. We saw some good slides at the beginning of this presentation talking about the critical role that it plays in stringent climate change mitigation, meeting things like our 1.5 or 2 degrees Celsius target. But what I want to focus on really is what we know, or what we think we know, about how carbon removal could be deployed in the state of California. So
Hey,
I'm going
Dan,
to walk.
so sorry to
Yeah,
interrupt. Would you mind making the screen a little bit bigger? We're getting some comments that's hard to read some of this text.
no problem. Is that any
Okay.
better?
Yes, thank you.
Okay, no problem. Thanks for the technical troubleshooting. So I wanted to speak about some evidence that we know about how we could deploy biomass carbon removal in the state of California. And this is a report called Getting to Neutral that was released in 2020. It found that, broadly stated, across biological and natural and working land-based carbon removal, engineered carbon removal, like direct air capture, and hybrid carbon removal, things like bioenergy with carbon capture and sequestration, that there was likely the potential for around 125 million tons of carbon removal at scale in the state of California in the near term. And that is, that was pretty similar to the gap between where we thought we could get in the 2018 scoping plan and carbon neutrality. Now, there's been a lot of updates to carbon neutrality legislation and California's climate change goals since the year 2020. But I was involved with a lot of scientists at Lawrence Livermore National Lab in particular to assess that opportunity. And I was I tried to find the amount of really residual biomass that might be available in the future from from the byproducts of forest management, the byproducts of agriculture, and the biogenic fraction of initial solid waste that might be available for carbon removal and could be used for carbon dioxide removal in the state. But it's really, we are seeing a broad range of approaches in the biomass carbon removal space being proposed and being scaled up. I'd be remiss if I didn't mention a few of them. Again, not all of these use lignocellulosic biomass. There are some proposals that focus on capturing CO2 from corn ethanol production, which ferments the sugars in corn in order to make ethanol as a transportation fuel. There are lots of projects scaling up around the Midwest that are focused on capturing the CO2 and sequestering that from ethanol biorefineries. We heard about biochar. But there are other approaches that people are starting to talk about. That includes capturing CO2 from the production of lignocellulosic fuels. That includes the direct injection of biomass and biomass-derived products underground, or the burial of wood. There are opportunities in the production of renewable natural gas to also capture CO2 and put it underground. And finally, we're also seeing lots of efforts to capture CO2, biogenic carbon from the pulp and paper production process, which is not particularly relevant in the state of California as we have no paper industry, but is progressing in the United States and starting to gain some scale.
And Dan,
So
just 30 seconds to wrap up here.
30 seconds, great. Okay, I want to discuss a case study on the way out. I think there's a real opportunity for to pursue co-benefits and secure climate benefits as well from using forest residues related to thinning California forests and reducing catastrophic wildfire risk. I've done some work on this. I'm happy to talk more about it. We think that there's an opportunity to stimulate innovative wood products, make sure that we're locking that carbon up in long-lived products, achieving carbon benefits, and really importantly, achieving wildfire hazard reduction. That includes 3 million acres of stand replacing fire over the next 40 years, according to our work. So I think this is just one example of where there are tremendous co-benefits in pursuing carbon removal in the state of California. Look forward to more discussion later. Appreciate it.
Awesome. Thank you so much, Dan. And I'm sincerely so sorry for having to cut off all the great speakers, but we have a lot of information to share today. So next up, I would like to invite up Dr. Shay Wolf. We will now hear a different perspective on biomass carbon removal, one that's coming up quite a bit in the chat. And I'm hoping that Dr. Shay will be able to address some of those same concerns. So Dr. Shay, while you start sharing your screen, I'll tell the audience a little bit about you. Shay is the Climate Science Director with the Center for Biological Diversity's Climate Law Institute. She provides scientific support for the center's campaigns to protect people and wildlife from the climate crisis. She has a bachelor's degree in biology from Yale University and a doctorate in ecology from UC Santa Cruz. Thank you so much for joining us, Shay.
Thank you, Bonnie. Hi, everybody. I'm going to focus on a type of engineered carbon dioxide removal that is being very heavily promoted and subsidized as carbon negative, and that's woody biomass energy with carbon capture and storage. And this specifically is using forest biomass to produce energy like electricity, fuels, and hydrogen, and to pair it with carbon capture and storage. And the claim is that this biomass energy is carbon neutral, so that putting some CCS equipment on the smokestacks will make it carbon negative, or achieve carbon dioxide removal from the atmosphere. But it's been very well established that biomass energy is not carbon neutral, and that putting that CCS on the smokestacks does not make it carbon negative, and instead that this leads to harms to climate, to the forest, to public health and safety, and to environmental justice. And so to understand this, I'm going to walk us through the climate and air pollution that is emitted at every stage of this BECCS life cycle. And it starts with logging and thinning forests. This is often heavy-handed with heavy equipment. And this thinning converts a very carbon-rich complex forest into a depleted forest that stores much less carbon and it has much lower ability to draw down CO2 from the atmosphere. And even if this thin forest is allowed to regrow, it takes a very, very long time for it to regain its carbon storage and sequestration potential. So this is lost sequestration. Now, the industry, the biomass and timber industry will claim, oh, we need to thin forests to prevent wildfire emissions. If we don't thin those trees, that they'll burn up. But a robust body of science has concluded and found that broad-scale thinning actually releases more carbon emissions than it prevents from being released in wildfire. And other research shows that the vast majority of carbon is retained in the forest after wildfire. And this is even in very severe fire patches. They combust less than 2% of the living biomass. So logging and thinning is the biggest carbon emitter from US forests. The industry will also claim that logging and thinning is needed for community wildfire safety. But the reality is most homes and lives that are being lost are lost in these fast wind-driven fires that are burning during extreme fire weather that is being made worse by climate change, these really hot, dry, windy conditions. And logging and thinning don't stop fire, and they can even make fire burn hotter and faster by creating those dry, open conditions. What we know is community fire safety retrofits work. That's focusing on home hardening, air filters to reduce smoke pollution, and vegetation work in the defensible space immediately around the home. So getting back to the BECCS life cycle, there is pollution from the transportation and processing. So that's trucking the cut trees, often very long distances, cutting, chipping, and drying, and storing the chips in these big piles that emit methane. And when you're making wood pellets, there's additional stages of pollution with the pellet mills making the pellets and then the pollution from shipping those pellets overseas to be burned. The most polluting stage is the combustion, gasification, or pyrolysis stage of converting that wood into energy. And what's being used today is biomass combustion to make electricity. And we know biomass combustion has so many harms. We know that burning wood for electricity, is more polluting at the smokestack than coal, and that's what this figure is showing, and that it increases carbon in the atmosphere for decades and centuries, even if you're burning wood residues or waste. There's lots of public health harms. There's lots of nasty stuff coming out, particulate matter, NOx, and carcinogens. This worsens environmental injustice. These facilities are often sited in communities already overburdened with pollution. There's lots of ecosystem harms, and this electricity is very expensive. It doesn't compete with wind and solar. It has to be propped up by public subsidies. So new kind of processes are being developed and promoted. This is biomass gasification and pyrolysis, and they're being billed as somehow clean and green. But like combustion, they emit climate pollutants and other pollutants. So if we take gasification as an example, where you're using high heat, steam, and oxygen, you are making gases. A lot of that is carbon dioxide, methane, these are climate pollutants, some hydrogen. It makes some liquids and solids that can be very toxic, and it produces a lot of air pollution. So the energy coming from gasification and pyrolysis, the electricity, the methane, or the hydrogen is dirty energy from a dirty process. So we return to the BECCS life cycle. There's pollution across every stage. So putting carbon capture and storage on the smokestacks isn't suddenly going to make this carbon negative. And this will be covered by another speaker in more detail, but we have lots of information about CCS. It's been very ineffective. It fails to deliver on its carbon capture promises. It's energy intensive. It has lots of risk of leaks and ruptures. It's unsafe. The CO2 pipeline ruptures and storage leaks can sicken and even kill people, and that's the example being shown in this picture here. It increases pollution. These projects target environmental justice communities. They perpetuate pollution. They are unnecessary, and they're so expensive. So I just want to give an example of BECCS in the real world. There's only one industrial BECCS plant in the US, this Archer Daniels Midlands plant. It has received hundreds of millions of dollars in public money, subsidies. It's storing half of its CO2 target. It's captured a small fraction of its emissions, and it's just been found that its CO2 injection wells are leaking because of a steel corrosion problem, threatening the atmosphere and groundwater. So this is a major problem for the CCS projects and BECCS projects going forward. I want to note that there's widespread opposition to BECCS. The Climate Action Network, which is comprised of 1,900 civil society organizations, highlights the unacceptable negative impacts. And scientists and economics experts, you conclude that this is not carbon negative. So I just wanted to conclude with some science and justice-based solutions to end mandates and subsidies for false solutions like BECCS, and invest in truly clean, renewable solar and wind energy and energy efficiency. And let's protect our forests to do what they do so well, is to draw down, to store carbon and draw it down from the atmosphere. Let's protect them and let them regrow. This is called afforestation. This is an important form of CDR that helps people, wildlife, and people and the forest. And then focus on community wildfire safety. Of course, it's a very important piece in terms of home hardening, air filters to reduce smoke exposure, and prioritizing these investments for disadvantaged communities. So thank you.
Okay.
There.
Thank you so much, Shay. Really appreciate that incredibly engaging presentation. And just to note that BECCS is one form of carbon dioxide removal with biomass that focuses on the production of energy. So at this point, we've heard these two different perspectives from Dan and from Shay. So I would like to invite Dan back onto the virtual stage, and we'll have just about 5 minutes here for a discussion between you two. I'd like to open it up to see if there are any questions that you may have for one another after hearing each other's presentations.
I mean, I have a question, Dan, in terms of the experts saying that this really isn't a carbon negative, BECCS isn't a carbon negative technology. And I guess more specifically, you mentioned the Getting to Neutral report, which you were participating in. And that report calls for this massive industrial build out of I think 50 to 100 of these sort of BECCS facilities, where you're going to be using a huge build out of CO2 pipelines that's going to inject the captured CO2 underground, largely in the Central Valley, in communities that are already overburdened with pollution. And we know that there's so many harms that can come from from the CCS. So I'm just wondering about your comment on how do we explain this to the communities? How do you do that?
Yeah, absolutely. And I think we have a lot to discuss, and probably a lot of areas of disagreement. But I actually would defend the carbon benefits of using biomass to produce energy. When we say that more CO2 is emitted from biomass than coal-fired power plants, that's relying on some really reductive science, and it doesn't differentiate between biogenic carbon and fossil carbon that we dig out of the ground. And moreover, in California, we're talking about using the byproducts of forestry and of agriculture and of our municipal solid waste systems. And I think there's a really clear story about taking that carbon that would otherwise decompose and locking it up in long-lived forms of carbon for climate benefits. So there's plenty to discuss about carbon balance and forest management, but I actually think that in California and in the Western United States, there's not only a strong climate case for doing that, but also a strong public health and public safety benefit. I would say, in regard to your other question, I think this is exactly what we need to be debating and what we need to be discussing as environmentalists who care about California's agenda-setting climate action. We have a set of existing old, relatively unprofitable, fairly polluting biomass power plants, largely from the 1980s, that exist in California. And I think we absolutely need to think about how we transition that into it to make sure that it reduces pollutions, to make sure that it pursues environmental and social co-benefits, to make sure that our communities are involved in these questions as we're moving from just big studies on paper to actually doing this in real life. So I would suggest that there's probably, even though we disagree on some of the science, probably a good deal of common ground between the two of us on what we're trying to do for the state of California. Oh, sorry, it looks like you're muted, Shay.
Yeah, I mean, I think that a lot in California, that there are, I think, at least 10 BECCS projects that are being proposed, either to make electricity or hydrogen, one to make methane. And a lot of those projects, like I said, are concentrated in Central Valley communities, and some of them are reviving biomass combustion plants that had been shut down because they were so health harming to the community, and they're being revived as like pyrolysis or gasification facilities, and somehow, with CCS, and that just takes, turns one bad problem into another bad problem. Like I
Yeah, I would say that I really do think that modern and efficient bioenergy technologies, moving beyond combustion, is an incredibly important part of doing this transition, right? And I do think that more modern systems like gasification and pyrolysis, particularly with those retrofitted with or fit with carbon capture and sequestration, really do avoid the vast majority of the air pollution issues that come from the existing biomass facilities that we have operating in the state of California. So again, I think there's gray area. We haven't done these things yet, but my read of the science is that these are solutions that not only achieve large carbon benefits but also avoid some of the harms that we see with the existing bioenergy fleet, particularly in the Central Valley of California.
Alrighty, and on that note, I want to thank both Dan and Shay so much for this discussion. It's a juicy one and we want more of it, but we do have other topics to discuss as well today.
Thanks, everyone.
And I also want to note that, we have understanding that we may not agree on everything, but we're having these conversations together, and that is a huge step forward in doing what we're all here to do, which is solving the climate crisis. So I really appreciate the discussion. Next up, we'll be hearing from Dr. Peter Saris, who will talk to us about enhanced rock weathering and direct air capture. Pete, please join us on the virtual stage and share your screen. Pete is a research assistant professor at UPenn and acting PI of the Clean Energy Conversions Lab and a senior decarbonization engineer with Carbon Direct. Wow, we really have some accomplished speakers with us here today. Pete also received his doctorate at Cleveland State University. With that, Pete, take it away.
Well, thanks so much. Hope everybody can hear me okay. I'm at an airport right now, so if you hear announcements behind me, I'll try to drown them out. I've been in climate space for a little over a decade now. I spend a lot of my time at Penn and Carbon Direct, really looking hard at engineered side of carbon management and carbon removal. And I'm here to talk to you about two technologies. The first is enhanced rock weathering. So let's get right into this. And I think maybe first we'll talk about what rock weathering is. And it's a simple premise in that when some rocks dissolve, they absorb CO2. We've observed this for a very long time. The problem is it takes a very long time. It's part of our natural carbon cycle. And we don't have tens of thousands of years to wait for this to happen naturally. So the enhanced part here is how can we make this happen faster? And how can we do that in a verifiable way? I think that is, part and parcel of a kind of responsible deployment of these technologies, that we have an ability to measure that they're doing what they say they're doing. So in this process, the enhancement comes through, and I'll use maybe sugar in tea or coffee as an example. Very easy to observe that crystalline sugar dissolves faster than the sugar cube, right? So that's a matter of surface area. So what they look at is taking rocks that have the right chemistry and breaking them into smaller particles, right? And so that can help accelerate the weathering process that can take in the CO2 from the atmosphere. The other thing that you look at, again, with tea is that it will dissolve faster in a warmer temperature, right, than it does in colder temperatures. So you can also look at climates and climate impacts. You obviously need water. The basic premise is that you can broadcast this over a variety of lands. To do this, you do want that moisture component to assist in the reaction. But we look hard at croplands because we also recognize that many of these rocks also have co-benefits to crop and crop yields. One of those happens to be calcium. Calcium is the same ingredient in lime. And so we know that farmers are already using lime as a pH stabilization agent in their soil. So you get this co-benefit on croplands in terms of this reactivity. You get the CO2 drawdown in a dissolved form, And the hard part of this is that CO2 then becomes a little bit hard to track, right? And so I think there's a lot of potential in this, again, for carbon drawdown. There's a lot of potential for co-benefits, particularly when it's used in an agricultural setting. But it is what we call an open system. And an open system just means it's a little bit harder for the science to track the ultimate fate. And again, it comes back to, we want to make sure that these things are doing what they say that they're doing if we're using them as climate solutions. The scalability is vast. When we talk about rocks, this is not the bottleneck. We will not run out of rocks to do this. Two of the major forms here, and please forgive the technical terms, the ultramafic and mafic, this is Earth's crust, right? You have way more, in orders and orders of magnitude, more rocks available than we need to store all the carbon that we'll ever need. It's just a matter of, are they readily available? Do we need to put energy into these systems to bring them out, right? There are some things we need to consider. This isn't all good. Of course, we shouldn't be talking just about the benefits. There are potential harms. There could be metals in here, so we want to be really careful about the chemistry and the sourcing of these minerals. Some of those metals are beneficial, some are not, right? There's also, these are silicates, and so silicosis can become an issue too. Questions here, and I'll get to sort of a general scalability at the end, but I did want to transition into another technology that perhaps is starting to become a little bit more mainstream in name, and that's direct air capture, or DAC. And we made a video, and I sent it to the organizers to be shared, that kind of walks through direct air capture as an idea. It is simple in theory, and that is it removes CO2 directly from the atmosphere with machines. You have CO2 dilute in the air, it will come in one side of this machine, and within that machine is sort of a filter of sorts with chemistry that can absorb CO2 and tends to not absorb other things. And so what emerges from the other side of that machine is not CO2 free air, but air with much less CO2 than was started. So it's a simple idea and premise. It's not a great idea because CO2 is so dilute in the atmosphere. We'll talk about the energy associated with that. So in step two, then you have to add heat or energy to desorb that CO2 in a very controlled way. And that's where we get into what to do with CO2. We talk, you could put it underground with CCS. That's not the only thing you could do with CO2, not the only way to lock it up. We look at reacting CO2 with rocks, again, to store that in sort of rock form on the surface. It is very energy intensive. It's an energy intensive, at least today, between 2 and 3 megawatt hours of energy. Just for reference, the average home uses 1 megawatt hour per month. Okay, so that's a tremendous amount, a ton of CO2. We talk about that a lot. In the atmosphere, that looks about like the size of a hot air balloon, right? So one of the energy intensive things that we do is we actually, besides drive it off of the sorbents, we will condense it and liquefy it, and it takes that volume down from a hot air balloon to the size about the trunk of a car, right? We want to store in that form because, again, space is limited. But because it's so energy intensive, we want to make sure that that energy is coming from the right places too. That energy should be low carbon in itself. It would be completely counterproductive to take all this CO2 out of the atmosphere, only to send it back because the energy we used was energy intensive. And then finally, I'll just add a slight, this came from the IPCC report. I don't agree with all these numbers. So status, technical readiness level, this is just a scale from 1 to 9, 1 being, I thought of the idea today, 9, it's really, really ready to go on what these technologies are. You know, they're going to be growing over the next, our investments, you know, today is really important to make sure that these are more technologically mature. The costs here are probably a little bit optimistic. What we're seeing, actual strike prices and purchase prices are maybe double of what you're seeing here in terms of the cost. And again, we're talking about many technologies here, but DAC, enhanced weathering, are kind of the third and fifth columns respectively. And you can see the mitigation potential, right? So, you know, 2 to 4 billion tons for enhanced weathering. There's lots of rocks. Rocks are not the limiting factor, sort of like a location of moving these rocks. DAC has a lot of potential. We saw that 5 to 40 billion tons. And the Road to Removal report that I was a co-author on, they found in US alone, you could do 14. I personally don't want us to do that much direct air capture. I don't think anybody wants us to do that much direct air capture or enhanced rock weathering. I think we're seeing that there are so many solutions, all with their own risks and benefit profiles, that this really should be more of a portfolio approach, and as they all come together, kind of get us out of business. So that's where I'll end my presentation. Look forward to
Perfect.
comments.
Thank you so much, Pete. Really appreciate all the ground that you covered in such little time. Next, we'll have our final speaker of the day, and that is Dr. Charles Harvey, who will also be talking about direct air capture. Charlie, please come on screen and share your slides, and we'll go ahead and get this started. While you do that, Charlie is a professor of civil and environmental engineering at MIT. He's known for his outstanding research in the field of environmental engineering, including carbon sequestration and storage. He holds a bachelor's in mathematics from Oberlin College and a master's and PhD in earth science from Stanford University. Charlie, take it away.
Okay, and what do I have, 7 minutes?
Yes, a little bit less now because we want to leave more room for Q&A.
Okay. So given that time constraint, I want to sort of talk about one main topic, and that is enormous opportunity costs of doing expensive ways to reduce emissions when there are other ways that the same money could be used to do a lot more good. And I'm going to kind of introduce this in maybe a peculiar way, which is my background in how I got into this 15 or more years ago. So around 2007, I was interested in pushing my research towards something that would reduce greenhouse gas emissions. And I know a lot about fluid flowing around deep in the earth. So carbon capture and sequestration seemed like a good thing to work on. And also oil companies had already started basically funding any academic at a prestigious institution who wanted to work on it. And so with a group of other people, and I was a small part of this, we looked at this, we concluded that the technical challenges were kind of not a big deal because it's been done for decades as enhanced oil recovery. CO2 is injected into the ground to push out more oil, which is basically the same thing. So we started a company to do it. It's very successful. We raised $200 million, successful in that sense. And we had a pitch. And you have to remember, times were quite different then. It looked like there was going to be a bipartisan agreement for a carbon tax or a cap and trade system. And coal seemed inevitable. It was the biggest source of power. It was growing. And just like oil and gas now, all the sort of wise heads in the room would say, well, you'll never reduce coal burning. So what could we do? Well, we argued coal is the biggest source. CCS is already a mature technology. The oil companies are already doing it, and it's the least expensive way to do it. Now, what happened is over the next couple of years, the price of renewable energy, the cost of renewable energy and energy storage plummeted. So we no longer had an honest business, elevator pitch. We could still make money if we did enhanced oil recovery, or if we just worked to harvest subsidies. And I'm going to talk a lot about that, but that's not what we wanted to do. So the company ended. And what I want to show with this video is argument that we were right. This is the Kemper plant in Mississippi being blown up. It's not an industrial accident. It was purposely blown up after consuming billions of dollars in government subsidies for clean coal. So this is the purpose was to capture CO2 from a coal-fired power plant and inject it into the ground. Now, why was it blown up? The answer is pretty straightforward. It's because if they actually turned it on, the amount of power required to separate the CO2 from the nitrogen in the gas and to compress it and inject it would have been enormous. You'd basically have to build another power plant to do it, or you'd have to greatly reduce the amount of power coming out of this plant. And that's for CO2 coming out of a smokestack at maybe, roughly 20% concentrations. And what I want to say here for direct air capture, exactly the same thermodynamics, the energy penalty, the penalty required to capture it and compress it applies, but it's much worse. Because CO2, it's high in the atmosphere in the sense that it's causing climate change, but it's a low, it's a trace gas essentially. So it's probably roughly 6 times more operating cost to remove it than from a smokestack. And some simple kind of calculations that you can do are, think of it this way: the cost to remove CO2 from the air caused by burning a gallon of gasoline is equivalent to $6 increase in the cost of that gallon. The way I'd like to describe the sort of opportunity cost here is that if we spend $500, which is at the low end of the cost of direct air capture, instead of, to do direct air capture, we can get 1 ton out of the atmosphere maybe. If we had spent that elsewhere on any number of other projects, well-known things, we could get 20 times as much. And so that difference in CO2 that's gone into the air by directing the money to DAC instead of something else leads to an accumulation of carbon dioxide over a long period of time that we're going to have to deal with far in the future. Right. And this is where I don't accept the argument that we need to do this because we're ultimately going to need negative emissions. By putting resources into it now, we're going to need a lot more negative emissions. Is my time up? I kind of lost track here.
Yes, if you could just wrap it up in the next 30 seconds or so, and then we'll bring you back on for questions.
Okay, because there's a lot more to talk about. But let me wrap it up with one simple figure here. And that is the biggest sort of counter argument to the work that we've been doing recently to sort of objectively evaluate CCS is that we should always do all of the above. We should use every tool in the tool chest to fight climate change, that we need this whole portfolio. It's kind of like serving, different varieties of food at Thanksgiving because different people will want different things. But that's not the case. Electricity is, electrons moving along a wire. There aren't different flavors. So I think this argument is wrong in a couple ways. And I sort of have some jokes here, but to sort of make that argument, if you think of this portfolio of things we could do, there's a surprising number of things that lie outside of what should be in all of the above because they actually increase emissions. And things like direct air capture, if the energy to do it isn't managed correctly, it actually increases emissions. So it shouldn't be in there. And then there's a whole bunch of things that lie outside of this toolbox, tools you shouldn't use because they're really lousy tools. You should pick the tools that sort of get the job done, not other ones, just to have more tools around. And we have excellent, I'm sure a lot of you know more about this than I do. We have a lot of excellent tools now to reduce greenhouse gas emissions. So I'll stop there.
Okay, thank you so much, Charlie. Really appreciate the presentation. And I know that we're all hungry for more conversation, and that is why we're having a whole series on carbon dioxide removal. So I really appreciate the speakers keeping their comments as condensed as possible, even though I know you have so much to share with us. So just for a couple of minutes here, I really quickly want to invite Pete back to the stage. And Charlie, if you have any quick reactions to each other's presentations. We'll just give this a couple of minutes and then move into Q&A with the entire panel.
Yeah, I mean, I think in a sense, Pete said something very similar to what I'm saying, that this is quite expensive, energetically, if not financially expensive, and that you shouldn't do it if you have if you don't have clean energy to do it. I might push back on that a little bit because in most cases, if you have clean energy, you've got better things to do with it. You can simply put it on the grid and displace fossil fuel energy in most cases, or you can do something else with it that has more impact than direct air capture.
Sure. I appreciate that perspective. I think I absolutely agree with the premise that's been stated by you. I think it's been stated by others that emission reductions comes first. There's no using any CDR really, and all CDR is subject to this in lieu of emission reductions. We shouldn't be doing that at all. We should be putting the vast majority of our energy and investment into emission reductions. And I think we're already doing that. I think last time I checked, 99%, if we look by share, is going to emission reductions. Do not create greenhouse gases in the first place. I think the reality is that we find that there are some instances where that's a little bit more challenging. We call them hard to abate sectors where we could avoid. That's where the CCS comes in. I know we're not trying to conflate CCS and CDR, even though there's some overlap. I think then CDR comes on at the end. I think we look at IPCC, we look at other agencies who are looking at telling us how much carbon removal we need to do. That's a significant amount, right? Of carbon removal. My fear is if we don't invest in some of these technologies today, they won't have time to scale for when we need them. The other response is the opportunity cost of clean energy going to reducing emissions on the grid. I wholeheartedly agree that that is a better use in carbon if you just look at the immediate impact. What that doesn't get right is two things. One, I think it discounts the opportunity in learning and driving the cost. I think we think that that is energy intensive and expensive today. That's precisely why we need to invest, because that's how we bring those costs down. That's how we bring that energy down. Secondly, we are finding opportunities. Geothermal is a great example where there are reservoirs of geothermal energy that aren't suitable for producing electricity, right? That could produce the thermal energy for direct air capture, right? So we're heeding this. I think we're acutely aware of the opportunity cost and trying to be responsible here. And we're constantly evaluating situations and deployment scenarios where we can check as many boxes as possible, including reduction of harms, right? First and foremost.
Okay, can I say one more thing? And I bet, I think Peter and I are in a lot more agreement. So I want to take this opportunity to say something a little bit to the side that I think is really important for groups like this. And that is how these things are subsidized right now. It's a practical issue and it's really important. They're subsidized in large part through something called the 45Q subsidy, which pays per ton of carbon dioxide produced and injected, right? So it doesn't pay for emission reduction. And this is what DAC, direct air capture, hopes to get their money from. Now, broadly speaking, I think we should all be very concerned about this because there's a big difference between subsidizing producing carbon dioxide and injecting it and reducing emissions, right? It actually makes coal more profitable because coal is a good place to harvest a CO2 stream to get the carbon dioxide for the subsidies. And a lot of proponents of oil and gas like this, and they confuse the issue. They say we need to subsidize these techniques, and then what really happens, in large part, where the subsidies almost all go, is for enhanced oil recovery. So the captured carbon dioxide is injected into the ground to push out more oil. Now, California is not going to allow that. They still allow enhanced oil recovery, but they're not going to allow that. And where most of the CO2 comes from that get the subsidies is not from burning fossil fuels either. It's from pumping up geologic CO2 to the surface, separating out some methane to sell it, and then putting it back into the ground to produce EOR. So I think it's really important to point out how basically screwed up the subsidies are. And a very useful thing to do would be to fix those subsidies and then kind of get into the niceties of which technologies are the best. And another thing, realize these subsidies tilt the playing field away from any technologies that don't produce CO2. So in the hard to abate things like steel or cement, if you don't produce the CO2, you can't get the 45Q subsidy. So if you have some clever electrochemical method, you're not going to get it. And that's another reason why this is promoted by fossil fuel companies. So that was kind of long-winded.
And Charlie, on that note, thank you so much. And I do want to note that we will be having an entire webinar on policy levers in which we'll talk about things like subsidies. So that's a great point that you make, and we'll have more discussion on that. I want to invite at this point all of our panelists back on the virtual stage for some questions that we're getting in from the audience. We have a lot. So we will try to get through as many as possible in the time that we do have. So if you can please keep your answers as succinct as possible. People are hungry for information. So one thing that I will pose to all of our panelists here is the question of durability. This is something that we haven't gone into too much in today's presentations, but I'm wondering if someone can start off by explaining the importance of durability and maybe a little bit about the durability in each of the approaches that you discussed. Who'd like to take that on first?
I'll take it on for geologic carbon sequestration. So interesting thing happened. Almost all of the subsidized CCS projects are for enhanced oil recovery, except for one, the Archer Daniels Midlands ethanol plant in Illinois. Just last week, it failed. It leaked. And we only know about that because it's the only one of the projects that's not for enhanced oil recovery. So it's the only one that has any kind of oversight. And it was basically a mistake, even that it was leaked by the EPA. So I would like to say that if you inject carbon dioxide underground, we can manage it and keep it there. But the evidence isn't good from this. And we have no idea if we were to increase the scale of this to gigatons is what's proposed, what those massive pressures, massive plumes with huge buoyancies would do. So I'm sort of not worried that that'll happen because I don't think we'll ever pay the money to inject that much underground. But if we did, it would be scary.
Thank you, Charlie. Akash?
Yeah, I think the one concept I do want to talk about from a durability perspective is, and I see it, the notion of long durability in, at least in the ocean-based space, is very prevalent, which is like, it has to be more than 1,000 years and plus. And I wonder if people are like, I come from banking and I've been talking to people who come from treasury management kind of constructs. And to me, carbon removal and associated carbon credits and all those things are essentially an asset to manage the emission liability. And the concept that, that comes to my mind just looking at other asset classes of risk is that there's a term structure to those risks, and emissions have a term structure too, right? Not all emissions are they going to stay in the atmosphere forever. Some will be there for a few years, 5 years, some will be there for 20 years, some will be there for a long, long time. And to me, the concept of durability needs to actually be matching that as to what type of emission are we trying to actually to neutralize, right? And so to me, just having a blanket 1,000+ year durability is your answer to all the emissions doesn't seem like the prudent approach.
Thank you, Akash. Pete?
Yeah, and on durability, I think that's a really important question to consider. And I think I don't like putting nature-based versus engineered solutions up against each other. I don't like to create that dichotomy. I think again there's a benefit in each case. The durability aspect, and it's not just durability; it's kind of the measurability and verifiability of that. For some of the engineered solutions are quite strong and have less uncertainty than other forms. Enhanced weathering, I kind of noted that there's some uncertainty how to measure that, but that the CO2 form that would reach the oceans, that's generally observed to be durable for millennia, right? And we need to talk about keeping CO2 out of the atmosphere for long periods of time. We talk about the risk of geological storage. The reason we know that CO2 could stay down there is because of the CO2 that Charlie mentioned, the Jackson Dome, the other natural CO2 reservoirs, right? This has been long studied. CO2 storage in the subsurface is a mature technology. We have not done it for the purpose in the class 6. And if you don't know what class 6 is, I understand there's going to be another webinar on storage specifically. So I don't know how much we want to get into that. here, but there's, you know, specific wells that you need to use to make sure that that CO2 doesn't leak into the groundwater systems. We're talking about ADM, and ADM was an interesting example where the leakage came from the monitoring well. And that was so not everybody agreed that they needed to put that monitoring well into that site because there are other ways to monitor it. I think the analogy is if you're baking a souffle in the oven, you're not looking through the glass window, you keep opening the oven, right? And that souffle doesn't rise properly, right? So this is essentially what happened. It's a good learning experience, but we have decades of experience in understanding risk mitigation planning for CO2 injection in the subsurface, including post-injection site care, right? And monitoring of 50 years to ensure that that CO2 is behaving. And I would encourage you to look through underground injection control program from the EPA, which did act exactly as it should in that instance, that shut that down when that was recognized.
Thank you so much, Pete. Does anyone else want to talk about the durability issue? Yeah, Dr. Shea.
Yeah, I mean, I think we're talking about the underground storage and CCS. I think that there's a lot of it is going to be injected in existing oil and gas fields, which have this really long history of like leaks and blowouts, like Aliso Canyon. The most kind of well-monitored, like scienced and studied fields in Norway, like they had problems, these two fields. Like the plume, the CO2 plume, once it undergoes, it's like once the CO2 is underground, you can't control it. You can just maybe stop injecting, but it went in all kinds of directions. It went up to layers, like toward the surface layer, you know, toward up in layers toward the surface that they didn't anticipate. It's going laterally. They had a lot of emergency situations and unexpected situations. And then you have like the pipelines too. And we know that like there's this like proposals to build like just thousands, tens of thousands of miles of like CO2 pipelines. And we know from oil and, you know, from gas pipelines that there are a lot of accidents, a lot of leaks and ruptures. And we know from the smaller amount of CO2 pipelines today that I think there's been like 75 public safety incidents, some of them leaks, and there was that big blowout that happened in Mississippi where people were hospitalized. And when that CO2 leaks, it's colorless, it's dense, it's asphyxiant, it can suffocate people, and people were unable, they had seizures, some people were foaming at the mouth, the emergency, like some vehicles get stalled out. I mean, there's like really big concerns about those issues. I don't think I mean, there are a lot of risks and dangers, and those things, there's the durability issue, like who bears the brunt of that? We need to keep that stuff underground for millennia. Who bears the brunt of that? It's probably not going to be the industry, it's probably going to be the public, you know. So the requirements are not there yet on like guaranteeing that durability, and we know from real world accidents that it's just very risky.
Yes, and I want to note two things there. One is that we are going to have a speaker from Satarsha, Mississippi, where the accident happened, on the next webinar. And I also wanted to note that Pete in the chat said that you can absolutely control CO2 underground. So I think that there are a lot of safeguards that are needed. But you know, there's a fine balance to strike there between ensuring that the carbon that is in the atmosphere for hundreds of thousands of years, the solutions that we're partaking in to draw that carbon down also addresses the long-term issue of keeping that out of the atmosphere. I quickly want to move to Charlotte. I know you had your hand raised for durability, and then we'll wrap up.
Awesome, thank you. Yeah, so speaking to the land carbon side, I feel like we have such a different set of problems when it comes to durability. And someone very kindly put in the Q&A session questions a really great paper that came out recently from The Guardian talking about the threat to the land carbon sink. So I just want to shout out that person. You know, when we talk about these land solutions, the durability depends on a certain amount of ongoing management. You know, if we plant forests, they're only as durable as protecting those forests long term. And if we add carbon to soils by doing a no-till practice, so you're not tilling up the soil, then if somebody does till up that soil 30 years later, you can lose all of the carbon that was accrued. So mentioning durability, I want to just emphasize that part of this is working very closely with communities and ensuring that we have a project that is providing the co-benefits that were guaranteed, that is supported by people. Because if we incentivize a farmer today to not till, and then 30 years later that incentive is gone and it's no longer working for them, we're not going to have the durability that we hoped for when we started the project.
All right. Thank you, Charlotte. And, you know, we have so much information here, so many great conversations to digest. Unfortunately, we are at time. I want to give a big virtual applause to all of our incredible speakers. Thank you so much for sharing your expertise and perspectives with us today and for rolling through all these conversations as quickly as we had to. And for all the great work that you're all doing to help us help out of this climate crisis. Really appreciate it. And thank you to the audience for joining us. I hope we're all leaving with a better sense of the portfolio of approaches that we have when it comes to carbon removal. As I mentioned at the very top, we will be having our third installment of the series on November 15th, during which we will be doing a deeper dive into the health and safety concerns surrounding carbon removal, some of which we touched on today. There's going to be a link in the chat to sign up for that. And separately, the Climate Center will be hosting a legislative wrap-up webinar on October 31st. We will also drop that link in the chat. And lastly, please join me, everyone, in thanking our co-hosts, Melissa Romero from California Environmental Voters and Diane Doucette from Project 2030, as well as the many Climate Center staff that helped make today happen. Thank you all so much, everyone, and have a great rest of your day.